Welcome back, everyone. We're- Today we're gonna learn the basic concept of classification. At first, we're gonna learn the concept of perceptron. Before talking about in detail, let's first talk about the concept of. Let's learn what the classification is. Last time we have learned the concept of regression, where our objective is to find best model that represent the relation between x and y. So here the x and y has we need to find best model that represent the relation between these data. So our objective is finding a best linear or non-linear model that represent these data. So here our predicted value of y can have any continuous value. But in contrast, in the classification, our prediction model predicts y with a discrete value. So that's the only difference that's the big difference between the regression and classification. In regression, our predicted value can have continuous value. So let's say if you predict the house price, then the predicted value can have like 10,000.2 dollars. However, in the case of classification, the predicted value should be a discrete value. So it's kind of finding a best classification algorithm to determine which class a new input should fall into. So here, from here we're gonna learn. We are gonna start with a binary class problem where only two classes exist. So let's say if you have a data like this, we can say only two class exist. So from the very starting point, we're going to start with a binary class problem. So it could be predicting value between 0 and 1. And later, we're going to extend to a multi-class classification problem, and this is just an extension of binary classification. So for that, we could use linear regression. And here, the threshold, the classifier, the threshold, the classifier output will be used, which means if anything over some value is say yes, else no. So if your predicted value are, let's say, predicted value should be in range from 0 to 1, and if your threshold is 0.5, and if your predicted value are 0.6, then this class will be fall into the class 1. And in the case of 0.1, then this value is under this threshold, so this predicted value will be fall into the class 0. So like this, by using that, we can use a linear regression to classify these values. So linear regression with thresholding seems to work. So for the classification, we will learn three algorithms, like the first perceptron, support vector machine, which is called SVM, and logistic regression. So later on, I will discuss in detail later on. So the objective of the classification is to find a classification boundary, which means, let's say, if you have these data, then the way our objective is to find these classification boundary. So over these area, we will make them in the class 1. and over this area we will let them fall into class 0. So let's say if you have a new data here, we will all agree that this data will fall into the class 0. So to determine that, we need to find fast classification boundary. So that would be our objective. So for that, let's first learn the very basic algorithm of perceptron. So to understand the classification problem, let's first take an example of the classification problem. So let's assume that that you are an employee at a bank, and let's say a customer comes to you to borrow some money. So, and let's consider this problem as a classification, whether to lend money or not. So for that, there would be a lot of input, right? So these input can be your the customer's age or their job and their average income and gender and height, etc. So for that, for these input, some should be very high weight to determine whether we should borrow money or not, and some is not important factor, unimportant factor like height or weight would be not important factor. So for that, for these input variables, which attributes of a customer, we need to take care of the weights to determine the final decision. So for that, by considering these value, which means by considering the weighted input, and by calculating the summation of these value, you will decide whether you will approve the credit or deny the credit. So in this case, if this value is more than the threshold, you will approve the credit, so you will allow them to borrow the money. And if this value is smaller than some threshold, you will deny to borrow money. So to whether decide so for that, you need to first determine the threshold. So in mathematical way, this problem can be written as like this. So for that, this value, which is the weighted summation of the input attribution, weighted summation of these input minus threshold, and determine the sign of this. So here the sign represent a plus, represent whether it should have plus or positive value or minus a negative value. So if these are the plus, then you will get a plus sign, you will get a plus or a positive value, and if this is a minus, then you will get a negative value. And for the threshold, it is our choice to determine the threshold. So in that, we can rewrite this as plus omega 0. So in the previous slide, we rewrite this mathematical expression for the classification problem, and in the last part, if we introduce additional artificial coordinate which has x0 is equal to 0, x0 is equal to 1, then this the final term can be included in this summation by letting the I is starting from 0 to d. And this problem, as we can see here in this part, can be understood as the vector summation or inner product. So in a vector form, the perceptron problem, it can be rewritten as like this. So in previous slides, we have learned that the mathematical expression for the perceptron or classification problem is nothing but hx is equal to sine, determining the sign plus or minus sign of omega transpose x. So perceptron works for linearly separable data, which means by determining the decision boundary, we can linearly separate these into two classes. So here we will call it as a hyperplane. So hyperplane will separate a d-dimensional space into two half spaces. So it is defined by an outward pointing normal vector, and here omega is also going to any vector lying on the hyperplane. So let's assume that, and here we're going to assume that hyperplane passes through the origin. So omega t x is equal to 0 with x0 is equal to 1. So in geometrical way, we can understand like this. So here the classification for perceptron problem can be understood like this. So if omega tx is equal to or larger than 0, then we will call this data as the class 1. And if omega transpose x is smaller than 0, then we will fall into this data into class -1 or 0. Let's say class -1. So from that, we can understand that the decision boundary can be a omega transpose x is equal to 0. So if this value is smaller than if this value is larger than 0, then we will take this data as class 1. And if this value is smaller than 0, then we will take this as a class -1. So from that, the important thing is, based on that, omega tx is equal to 0 can be a decision boundary or hyperplane. And let's see the meaning of the omega. So for that, let's first assume that vector p and q are on the decision line. So let's say 2 points here, P and Q. So by knowing that P and Q are on the line, then we know that GP and GQ is equal to 0. So from that, by subtracting these equations, we can obtain that omega t p minus q is equal to 0. So for that, this is nothing but the inner product between omega and p minus q, which is on this line, is equal to 0. So that means omega is normal to the line. So that means omega and the line, the boundary line is orthogonal. So by knowing the omega, we can know that the direction of the line. So that's the very simple meaning of the omega. Then the question is how to find omega. So from the geometrical point of view, we know that all data in class 1 has the gx is larger than 0. And for all data in class 0, where y is -1, the gx is smaller than 0. So by knowing the omega and the decision boundary, if this data has in this way, we know that this would be fall into class 1, and for these data will fall into class transfer into class 0. So let's see how the perceptron algorithm works. So as we have discussed, the perceptron implements the mathematical expression like this. So hx is just nothing but the sign of omega transpose x. And for the given training data set, we have a labeled data set. For n labeled data set. So for a given x, we already know the answer of the class. So, and these classes are only a -1 or 1, indicating binary classification. So for this problem, let's see how the algorithm works. So for that, firstly we need to pick a misclassified point. So for that, the meaning of misclassified is that what we predicted value is not exactly the same as the original target, the answer of yn. So for this misclassified point, what we need to do is just update the weight vector by using the y plus yn and xn. So let's see how this works in geometrical way. So for the case where the true value is +1, the meaning of misclassified point is our prediction is -1, right? So for that, we need to change our model to predict that this value as equal to the +1. So in this state, the meaning of this one is, let's say our x is here and the omega is like this. And as we discussed earlier, the omega indicates the direction of the decision boundary. So by plotting the perpendicular line, we know that this is our current decision boundary. Current decision boundary. So here we know that our prediction, the x value, is in this way. So the sine omega t x is -1. But actually we know that true value is +1. So for that, let's update the weight, which is equal to omega plus yn and xn. And here, this one is omega plus yx. So by using the vector addition, the updated value would be like this. So the blue line would be the updated weight vector. So for that, by plotting the perpendicular line to this, let's say, by plotting perpendicular line to this blue line, this would be our updated decision boundary. So as you can see here, in this case, this value, the misclassified point, would be now correctly classified. So here, in this case, with the updated weight vector, the sign of this would be the +1. And in the case of another case is also similar. When the true value is equal to -1, then by updating this omega to omega plus yx, we can change the decision boundary, so we can change the location of the x. So by using this algorithm, we can correctly make the decision boundary by updating this. We can correctly decide the decision boundary. So based on the idea how the perceptron works, the iterations of perceptron is very simple. Firstly, we need to randomly assign the omega and one iteration on the PLA. So perceptron learning algorithm is just updating the omega with omega plus yx. So for the misclassified training point. And by updating for the iteration, let's also pick a misclassified point and just iteratively run a PLA iteration on it. So that's it. This is a simple diagram of perceptron. So by getting multiple inputs and by multiplying the weights, we need to calculate sine of omega x, omega transpose x. And for that, we are calculating our predicted value, and by comparing this predicted output with the actual output, by knowing the whether it's correctly classified or misclassified. For misclassified point, we need to update this weight value. So by keeping this iteration, we can properly allocate model to predict a proper value. So the loss function for perceptron is finding a max value between the 0 and minus yn dot omega transpose xn. So the loss is equal to 0 means the prediction of perceptron is correct. So here, and if the loss is larger than 0, then that means the perceptron is misclassified. So by calculating this loss function, we can update the omega. So based on this idea, let's implement this perceptron algorithm in Python code. So for that, we need to first import an NumPy and Matplotlib library as usual. And let's firstly generate some random data for training data generation. And if you plot these randomly generated data, you can clearly see two classes. The data classified into two classes. And as we discussed in the previous slide, for the GX, by introducing additional artificial coordinate for x naught, which is just 1. So here we can rewrite GX like this. So for that, x is nothing but just horizontally stacking x naught and x1, x2. So for that, we need to horizontally stack these x value, and horizontally stacking this x value, and y is just exactly the same as. And by treating this x and y as matrix, all the things for preparation is done. And the only algorithm for the perceptron is updating omega for this misclassified training point. So for that, for the n iteration, we need to first check whether this one is correctly classified or misclassified. And if this one is misclassified, that means our the true value and the predicted value is not the same. Then we need to update the omega for the omega plus y transpose y times x. So by updating this, this one is all the Python code for perceptron algorithm. So after finishing the perceptron algorithm, let's plot the result. And here are the result. And as you can see here, by updating this decision boundary for misclassified condition, we can see that the decision boundary becomes now all classify all the data for class 1 and class 2. And of course, as we have learned the scikit-learn for machine learning framework, we can also implement a scikit-learn for perceptron. So for that, the pre-processing is exactly the same. And for scikit-learn, we need to import from scikit-learn, we need to import a linear model. And from the linear model, let's use perceptron function. So for that, our classification model is let's designate the classification model as linear model dot perceptron. And by using similar to regression, let's use the fit function. So clf.fit will give a result of will give a fast fitting model between x and variable y. And by using clf.predict, then we can see the classified result. So in summary, we have learned the concept of classification, and among them we first learned the concept of perceptron. So perceptron finds one of many possible hyperplanes separating the data if one exists. That means, let's say for these data point, there would be a lot of hyperplane, but among them, perceptron finds one of them. So of the many possible choice, which one? You may ask, which one is the best? And so for that, we need to utilize distance information. That means from these models, we can intuitively think that we want the hyperplane having the maximum margin. That means among the second one would be the best hyperplane having best margin compared to this group and this group. So large margin leads to good generalization on the test data. So that means if we have the hyperplane for this, then we have very small margin to this. So for example, if we have a new data point like here, we can intuitively think that this would be this point would be 4 into the class 1. But if you set this as a decision boundary, then this new point would be predicted as the class 2. So for that, for the generalization, we need to select the hyperplane with the maximum margin. So for that, we will see this formally for when we discuss a support vector machine, which I will discuss later. So that's the summary. So we need to utilize distance information from all data samples, and perceptron will be shown to be a basic unit for neural networks and deep learning, which we will be discussed later on. So as we discussed earlier, from the idea to find best hyperplane, from now on we're going to talk about the support vector machine. Support vector machine, the main idea behind this SVM is to separate classes as correctly as possible. So for that, we're going to select the hyperplane with the maximum margin. Before talking about in detail, let's first discuss the distance from a line. So when we have the gx is equal to 0, and then we need to find a distance between gx is equal to 1 and gx is equal to -1. And suppose let's say we have two additional line of gx is equal to -1 and 1. And for that, from that, suppose we have 2 points at x1 and x2 that satisfy gx1 is equal to -1 and gx2 is equal to 1. And by substituting this equation into this, and by by sub by sub, sub by subtracting from this equation to this, we obtain this. And from that, the left hand side means just the inner product between the omega and x2 minus x1. And from that, if we rewrite this inner product, then this is nothing but the omega 2 over the magnitude of omega. So from that, we can conclude that the distance between gx is equal to distance between these two lines is 2 over omega. So we can conclude that this one is just the half of this. So it would be 1 over the magnitude of omega. By keeping this in mind, let's see the idea of SBM. So the idea of perceptron is finding best omega, not the best, finding omega such that x satisfy this condition, which means omega transpose x is equal to 0. But in the case of SBM, the objective is finding omega such that that satisfy these conditions. So that means for the x that belongs to C1 class should have omega transpose x should be larger than 1, and in the case of x that belongs to the class C0 should have omega transpose x smaller than -1. So let me briefly explain the idea between the SBM and perceptron. So let's say we have data points like this. So here, let's say this one is just class 1 and this one is class 0. And the idea of perceptron is finding a decision boundary that satisfies omega transpose x is equal to 0. And let's say this one is the direction of the omega. And in the case of SBM, the idea is finding omega that satisfies this condition. And this condition is nothing but finding the model with, let's say, omega transpose x is equal to v, and this one is omega transpose x is equal to -b. So let's write this one is -b and -b. So by finding this line, our condition is finding x that satisfy. So for the class 1, we are having omega transpose x should be larger than b. And in the case of the data point that belongs to C0, our condition is omega transpose x should be smaller than -b. And of course, between this line and this line, the distance is like this. So from that is idea. So the idea of perceptron is finding this line, but idea of SBM is finding these. So by doing that, we are now free. We are now have some band. So that's why I wrote it as decision band. So when we rewrite this idea in mathematical way, we can write this. So for that, now we have some marginal space, and that's why we call this as a decision band. So let's implement this idea for in Python. So for that, let's first generate some data for classification. So here we have data points which are indicated in red as C1, and the blue dot indicates the C0 class. And here by plotting this line, this one is the line for omega transpose x is equal to 0, and here these two lines are the marginal space. And from that, let's learn how to formulate this problem to optimization problem. And of course, we have only we have for simplicity, we are considering the case for only two features, and let's say n data belongs to C1 in training set and n data belongs to C0 in training set. So in total, we have n is equal to n plus m data points in training set. And by rewriting x and omega like this, our objective is finding omega and omega 0, which are unknown variables. Then our objective for the optimization is minimize anything or something which are subject to this constraint. And as you can see here, the class for the data points with n data for C1 should have the value larger than 1, and for the m data points that belongs to class C0 should have smaller than -1. And of course, both are the same, where here we add additional coordinates, artificial coordinates for x0 is equal to 1. So from the expression that we formulated optimization problem, of course, by using CVXPy, we can formulate this optimization problem simply. So by using CVXPy, we need to set a variable as 3 by 1. And of course, the objective function can be something or anything. So our objective function is just by letting just 1. And the constraint should satisfy this condition. So for the data point x1 should x1 transpose omega should be larger than 1, and x0 times omega should be smaller than -1. And by setting a CVX problem with objective and constraint and solve, we can obtain the proper omega value. And by using that CVXPy code, you can see the result, which is indicated in green line, and we can clearly see that this green line is inside this decision band, so it properly indicates the decision boundary with proper margin. And from now on, let's see the case where outlier exists. Of course, in the real world, you may have some noise or errors or also called outlier that do not accurately represent the actual phenomena. So in this case, this is also called not linearly separable case, so linearly non-separable case. So let's see, there are some outlier. Let's assume some outlier exist. And if you use exactly the same code for the optimization problem, then you will get the none value. So that means no solution that separate this. So no solution for hyperplane exists. So in that case, we have to allow some training example. So these should be misclassified. So from that, we want to, but in that case, at the same time, we want their number to be minimized. That means we know that this one is the proper this line is proper the predicted value, but by using this we have many misclassified point. So our objective should be minimizing the misclassified point. So when the outlier is included, we knew that the data is non-separable. So in this case, we need to relax the above constraint. So for that means we need to relax these constraints. So this one was too strict. So we were not able to find a proper decision boundary or decision band. So in this case, we need to select variable u and v where all are positive. And for this sentence, I'm going to explain in detail in the next slide. So our problem is that our data is like this, but there are some outlier here, so we were not able to split. We were not able to find these decision boundary or decision band, and so in this case we need to modify our objective problem. So for that, we need to introduce additional select variable, which is u1 and u2. So for that means for this misclassified, this one is class 1 and this one is class 0. And for this misclassified data, or for this outlier point, actually this should be the data should be included in the class 0, but due to the outlier or some errors, these are located here. So actually this one has the labeling for, let's say, labeling for the 1, but actually this one is not 1, so the target value should be -1. But in the case of, so when you calculate for this data, when you calculate the omega t times omega transpose x, then this one will give you the -1. So, but we need to relax, or we need to allow this one is misclassified. So for that, we need to introduce additional term so that so that this one makes a negative value. So in that case, we are relaxing, or we are allowing them to misclassify it. So by doing so, we are now able to find proper decision boundary like this. So we are by adding additional term u and v, we are adding by additional term additional variable u and v, and our objective function would be should be changed to minimize these terms. So this allowing term, like by adding this line u1, this data can be classified to class 0. So, but at the same time, we need to minimize u1. So of course, this one will also allow this data should be classified into class 0. But by minimizing this u1, our generalization, our model, the accuracy model will be improved. So our objective function is just minimizing the absolute value of u1 and v1. And when you express this optimization problem in a matrix form, then you can simply simplify this one, like minimize this equation which is subjected to this relation. So of course, by using CVX-Py2, we can implement this optimization problem in Python. And as you can see here, when you plot these equation, you can clearly see the proper decision boundary with this proper margin of decision band. So from here, we can see that hyperplane or the decision band is not accurately represent the division due to the outlier, but still still can divide these two data into two classes. But you may have questions. Can we do better when there are no data on outliers? Yeah, but in that case, we need to look beyond linear programming. That means here we use this linear line. So this is kind of a linear classification. But for that, we need to look beyond linear programming or linear classification. So instead of that, let's use a large margin for the good generalization on the test data. So the idea of maximizing margin is just the idea of finally it is support vector machines, which is called SVM. So as we discussed earlier, we know that how to measure the distance between the margin and the GX is equal to 0. And for that, the margin can be calculated like 2 over the magnitude of the omega. So to maximize the margin means that minimizing the magnitude of omega. So here we're going to use additional gamma as a weighting between the following. The first one is maximizing the margin, and the second one is measuring the hyperplane that has few errors. So for that objective function, we can rewrite this in a mathematical way. So here is just exactly the same as minimizing omega 2 plus gamma and blah blah. And actually, we know that this one is just the error. So minimizing error, but at the same time, we need to maximize margin. And when you include this optimization problem in a CVX-Py, here we're going to use a gamma, and the result clearly see that the decision boundary with the maximized margin can be found. So here, of course, there are some outliers, but we can think that this one is a reasonable and very good approximation for the decision boundary. And of course, as we learn the scikit-learn, we can also implement this SVM using scikit-learn. So for that, we first need to import SVM from scikit-learn, and the idea is classification, just using the model as svm.svc, and by just fitting this xn labeled y. Then when you use crf.predict, then you're gonna see the result which has proper omega value, and the result is what we already know. Yeah, so far we have discussed the linear separation. That means for given these data, our objective is finding a linear line or linear plane that can divide or that can split these data into two classes. However, here we're going to talk about finally extend this idea for classifying non-linear separable data. So for that, when we think about this example, you can see that it is not easy to divide this data by using a single linear line. So here, no linear separator exists for data. Of course, you're gonna think that we can use these line, but of course this one is non-linear, so we need to think about how to divide this idea. And here, instead of directly use this data, let's now map this example as x is equal to x squared. That means let's add additional data points. So here, for by adding additional coordinate, we don't need to require additional information. Instead of that, let's just add additional x's, that is x squared. So here, by doing so, data now becomes linearly separable in the new representation, like this. So when you plot this data in the x and x squared axis, you can clearly see that this quadratic information. So by doing so, we now have a linear classification boundary. So by doing so, we can split these two data into two classes. So here, linear in the new representation means nonlinear in the old representation. So the key idea is just changing this data to this expression by using the mapping. And similarly, for the other example, like for this one, we now intuitively think that we can divide these two data by using this nonlinear classification. But as we discussed, there are no linear separator exists for this data. So instead of that, we need to divide it using nonlinear classification. And for that, we also need to convert this data by adding additional data points. So for that, let's now remapping this data by these three terms. So here, each example now has 3 features instead of 2. And by doing so, we are now by plotting this new data in the G1, G2, and G3 axis, we now clearly see that these data can be transformed, and by doing so, we can find a linear plane that can split these data into two classes. So by doing this mapping, data now becomes linearly separable in the new data representation. So here, for the process for the mapping, we want to capture nonlinear patterns in the data. So here, as we discussed, for the nonlinear regression, input and output relation may not be linear. And similar to that, nonlinear classification problem classes may not be separable by a linear boundary condition. So to use a linear regression like linear SVM or perceptron that we discussed earlier, it's not rich enough. So for that, if you want to use this linear regression, we need to map this data for higher dimension where it exhibits linear pattern. So by applying this linear model in the new input, new feature space, we can do the linear regression, linear classification. So mapping is just nothing but the changing the feature representation. And for the process for the mapping, we're gonna introduce new terms for corner, that is make a linear model work in non-linear settings. Yeah, so finally, let's implement this classifying nonlinear separable data using Python. So for that, let's take an example of this data that has that is a binary classification problem. Of course, if you see this data, you're gonna say that the decision boundary can be represented like this. So this one is actually nonlinear boundary, and let's solve this problem using linear classification problem. And for that, we need to take additional step for changing this data to mapping another coordinates. So for that, let's prepare this data, and then let's change this data to this mapped data G. And after that, the other process is exactly the same as the linear classification that we have discussed. So for that, let's define the objective function for the SVM that minimize both the magnitude of the omega and the error, hyperplane error, that's subject to this constraint. So let's define the constraint, and let's solve this problem by defining the problem. So from the data, we can clearly see the result that has the SVM result that has. So of course this plotted region does not represent a linear process, but what we have done is just exactly the same as linear classification. Yeah. So that's what we have discussed today. So far we have discussed the basics of classification. So for that we have learned two classification algorithm for perceptron and SVM. So you guys should know the difference between the perceptron and SVM, and you guys should also know how to implement these algorithms using Python. Yeah, that's it for today's lecture, and thank you for listening.